Hello there, children. Today we are going to work on section 3.2, logarithmic functions. Now, the question you might be asking is, what the heck is a log function? And why are we even doing this? So, why the heck are we doing this? Well, let's look at the inverse of an exponential function. So here's my exponential function, and I want to take the inverse of it. Remember, take an inverse, we flip x and y. So I take this and I flip x and y, their positions, right here from here, and I now want to solve for y. And therein lies the problem. I can't solve for y because I would have to take the yth root, and well, that's not going to work. I would end up with something like this. That's all well and good. Then I have to get y out of an index. Yeah, that's not gonna happen. So we need a construct by which to take the inverse. So this construct, if we have the following exponential function, it's on page 172. This is the following log function. Now, how it works. First off, to have a logarithmic function, you need to have the word log. Notice the base a of my exponential is also the base of my log function. And I simply take y and x and flip-flop their positions. X is isolated over here. Now y is isolated over here. It is read as y equals log base a of x. That is how we read this particular problem. Now, a couple of important things. We need to be able to switch back and forth between log and exponential form. This is exponential form. It's got an exponential. This is log form. It contains a log. If it's log form, it contains a log. Pretty simple. How do I switch back and forth? Well, if I want to go from this exponential to a log form, I need to first write the word log. Done. Then, the log base what? The base of my exponential was 9. The base of my log is 9. And then the 7 and the x flip-flop positions. Tie and dot. Which if we're trying to solve, which we will in later sections, this will be easier. Notice here, 9 to what power gets me 7? Don't really know. This x is now isolated. I could use a calculator on eventually. Over here, to turn it from log to exponential form, we have to get rid of the word log. What's the base of my exponential going to be? 5. It's the base of my log. 5 to the what power? 17y equals t. This is isolated. Now the t is isolated. I need to be able to switch back and forth between each of these forms because it will help me solve later down the road. Alright, some key important concepts here. The log base b of 1 equals 0. Why is that, you might ask? And remember, b must be greater than 0 here, just like the base of my exponential function. It has to be bigger than 0. Why? Turn this into an exponential. B to the 0. What's adding to the 0 power? 1. So you see how we took a known property, anything to the 0 power is 1, and I wrote the log equivalent of it. That's all these are, folks. The log base b of b equals 1. How do I do that? Easy. Turn this into an exponential. B to the first equals b. That's a known property. Anything to the first power is in of itself. Third property, a little bit trickier. The log base b of b to the x equals x. Turn this into an exponential. B to the x equals b to the x. So what that means, folks, is this. This is just taking a known property, that's obviously something equals itself, and writing the log equivalent. So essentially, if you have the log base b of b, whatever its exponent is, this exponent here is 1, that's going to be my answer, which is really important for us later on. And lastly, this is interesting, b to the log base b of x equals x. So that's pretty interesting. And we have a equivalent of that. Taking the exponential of this, these two things cancel out, which is wonderful. That's a log b to the log base b. Those would cancel, leaving x equaling x. Two quick notes here. Two special kinds of logs we have. Your calculator has both of these on there. You need to go ahead and try to find them on there. The first one is the log base 10 of x, which is just log on your calculator. So you see the log button, it's called the common log. It's the one that shows up most commonly. So remember how this exponent is 1 here, that coefficient is 1. Anytime you do not see a log base written, see the word log and no base, it is assumed to be 10. It is called the common log. The next one's a little trickier, and it brings back our function e. The log base e. Too many letters there. So when the French were dealing with this, they called it logarithm naturel. Well, guess what? Logarithm naturel got shortened to ln, which is called the natural log. So anytime you see ln of x, or the ln button in your calculator found near the e of x button used in the PERT formula, you in fact have the log base e. So your calculator can do base 10 and base e. It is important to note that. One thing to note, we can do logs even without our calculators though. Log base 4 of 64. How the heck do I do that? Well, guess what? I want to know 64 is 4 to what power? And if you recall, we'll pick a different color over here. We'll pick yellow. If you recall, and you should, log base 4, 64 is really 4 to the 3rd power. And guess what? This uses our wonderful and glorious log properties. The answer is just 3. Using our 3rd property of logs that we just had previously, this becomes 3. The log base 4 of 4 cancels, and I'm left with that exponent right there, which is wonderful. Another tricky one, we have this. We have the ln of e to the negative 13. Now you might be asking, how the heck am I going to do this? Well, remember, however, the following. ln is really the log base e. Now, I am showing you this just to show you how this property works. For the record, it is inappropriate to write the log base e. You should always write it as ln. But if you notice here, look the same as the last problem. The log base e of e, the 3rd property we had, that cancels out, and negative 13 falls down as my answer. Ta and da, which is wonderful. Now, just as an aside here, looking at this, the log base negative 2 of y equals x. Can we do that? Let's turn this into an exponential function. The base would be negative 2. My exponent would be x, and that equals y. However, if you recall from section 3.1, this cannot be done, not allowed to be done, for I have a negative base. Do you think that's a coincidence? No, 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 no. It is not. I cannot have a negative base of a log the same way I cannot have a negative base of my exponential function. They go hand in hand. Now, what are we going to do with logs in this section, you might ask? Well, we are going to graph them. But first, we need to talk about logarithmic growth. Just like we had exponential growth. What does that look like? It looks like all of this. Alright, so logarithmic growth. It's growing as it goes up and to the right. Notice there, no matter what my base is, provided my base is bigger than 1, my wonderful and glorious intercept here, the x-intercept, is always going to be 1, 0. Now, notice my domain and range. If you remember our exponential functions, and exponential growth had a domain of all real numbers. It had a range from 0 to infinity. just not equaling 0. Well, guess what? Remember, because a log is the inverse of an exponential, it would stand to reason that all my things would flip-flop. So look at my domain, from 0 to infinity, just like the exponential range was. Look like the range here, negative infinity to infinity. This graph goes up and down forever, just like the domain of an exponential. It doesn't cross the y-axis, just like an exponential didn't cross the x-axis. Its x-intercept is 1, just like an exponential had the y-intercept of 1. The asymptotes flip-flopped. There are still no mins and maxes. And the end behavior here, remember, as x goes to infinity, y is going to go to infinity. And as x goes to negative infinity, y is going to go to negative infinity. Now, if you notice here, it says as x goes to 0 from the right, because it's not, you can't really get to negative infinity, but it's okay to write this notation. And it's continuous from 0 to infinity. I can put my pencil down here at 0 and graph it that way forever. So that's not overly terrible, right? We can deal with that. It's just the inverse of an exponential growth. So if I drew an exponential growth up here, pardon my terrible drawing, it's kind of reflected around the line y equals x, which we talked about for inverses before. If we have exponential growth and logarithmic growth, we also had exponential decay and logarithmic decay. Remember, that's my bases between 0 and 1. The same with exponential decay, the base being between 0 and 1. Well, guess what, folks? What's the only thing to change here? Let's look. The domain didn't change from the last problem. Neither did the range. Neither did having no y-intercept. My x-intercept didn't change either. I didn't change my extrema. I didn't change my asymptote. The end behavior was the one to change a little bit. So as x goes to infinity, y is going to go to negative infinity now. Look how it's going down forever, slowly but surely. And as x goes to negative infinity, or to 0 here in this case, y is going to go to infinity and beyond. That is the only difference, and even it's continuous on the same grouping as well. So folks, the only thing different than a logarithmic growth and decay is the end behavior. It still has the same domain and range, still has the same x-intercept, still has the same asymptote. It just goes, instead of one goes up, one goes down like that, which makes sense if you were to draw an exponential decay here. Now you are ready to tackle graphing problems with transformations, which we will do eventually. And guess what? The same that hold true for the exponentials are going to be the ones that hold true for the logs. So get excited for that. Oh, happy days are here again. Go henceforth and do. Whoop, whoop.